And so today, what we're going to do is we're going to study what I'll call like the web.
We don't see your
yes, of course.
document.
Web of NP-completeness recordings. Let me just go ahead and share the screen just a second. Right. All right, so do you see it now?
Yeah. And you started recording?
Yes, I have. Yes.
Okay.
So the web of NP-completeness, I said recordings. What I meant was reduction. Reductions. And this is really like, in some sense, the big power of the theory of NP-completeness. Like this is its greatest success story. And it's all based on, I may have even written this claim before. I will just write it again. So this crucial lemma that says if L is NP complete and for some language M in NP, L reduces efficiently to M, then M is NP complete. And I leave the proof as an exercise, and you'll see that the closure of polynomials is crucial. Right? The closure of polynomials is crucial because basically it says that if L is NP complete, you can reduce any language in NP to L, and then you can just chain the reductions together, and that chaining will again be an efficient reduction, right? Because the running time will be a polynomial of a polynomial. So now this gives us a tool to prove NP completeness instead of using a Cook-Levin type reduction. So Cook-Levin did the hard work by finding some language that was NP complete. And so we started with SAT being NP complete, we used normal forms, and we used various tricks with Boolean formulas to prove that 3SAT is NP complete. And now using that, we will show that a plethora of problems are NP complete. And this web of reductions will suddenly sort of add to our knowledge of various different problems. So I'm going to start with what I think is a simple but very cool reduction. And so I'll say the language Clique is NP complete. So in these proofs, I may not write out all the details in full. I might not give you all the details in the sense that I might not work out everything in full formalism. I'll just draw out the construction, and hopefully, it should be apparent that you can fill in the details. And the reason I'm doing that is because I would like to cover as many reductions as I can to show you sort of, the kind of variety of problems that are NP complete. So just to remind you, what is the language Clique? So Clique is sort of, you should think of it as a pair, G comma K, where G has a clique of size K. And again, like this is just a simple undirected graph. Okay, so this is just a simple graph. So here's the proof. So it should be apparent that Clique is an NP. And I think we even discussed this when we were discussing NP, the notion of NP in terms of verification. So Clique is an NP, easy to verify that. And now what we're going to show is we're just going to reduce SAT to Clique. We're going to reduce 3SAT to Clique. Okay, so we're going to start with some phi. Okay, and I'm going to write phi, I can write in the following form. I'm going to call it Z1 or Z2 or Z3 and Z4 or Z5 or Z6, so on and so forth, where each Zi is a literal and multiple Zi's may be the same literal. Right? Does that make sense? So it could be the case, for example, maybe this is x1 or x5 or x10 complement, or the negation of x10, not complement, sorry, the negation of x10, and z4 may actually be the negation of x1 or x10 or x20, so on and so forth. So I'm just going to call this z1, I'm going to call that z2, call this z3, call this z4, z5, z6. So I'm just giving these things names, and note that x1 has been given the name, or rather z1 corresponds to x1, z4 corresponds to x1 complement. Further down, it could be that I'll say z7 or z8 or z9. This could be x1 yet again, but I'm just going to call it z7, right? So this makes sense. So I'm just going to convert this to this representation with this labeling. And now here's how I'm going to construct the clique. I'm going to construct a graph where the vertex set is actually going to be all the z's. I'm going to tell you what the edges are. So what I'm going to do is I'm going to create blocks of 3 vertices. So z1, z2, z3, z4, z5, z6, so on and so forth. Okay, so these are the vertices. So essentially, for every occurrence of a literal, not for every literal, but rather even every occurrence of a literal, I'm going to construct a vertex. Then, here's how I'm going to create edges. So for zi and zj in different groups, and a group you can think of as just a clause. Okay, zi, zj is an edge if and only if, or actually I'm defining this, so it's if zi is not the negation of zj. So note that this is some literal and this is another literal, and I'm just going to connect them if one is not the negation of the other. So they may be the same literal, they could be completely different literals. When they're different literals, I will definitely connect them. So the only time I do not connect them is when one is not the negation, or one is the negation of the other. That's when I don't connect them. Otherwise, I connect them. So this is going to create some graph here. Okay. Now, it's conventional over here to use, so there are m clauses here. So there are m groups, right? There are m such groups. Now, note that, now here's the claim, sort of the main sort of technical claim is that phi is satisfiable if and only if G has a clique of size m. Okay? Phi is satisfiable if and only if G has a clique of size m. Okay? Do you see why this is true? So let's start from the easy side. Let's prove one side, which is the if part. Suppose phi is satisfiable. So C is so there is a satisfying assignment. There is a satisfying assignment such that for all clauses, so or I should say that for so note that the way this is structured, the kth clause has the z vertices are going to be 3k plus 1, 3k plus 2, and 3k plus 3. So I'll say that, you know, for all k less than or equal to m, sort of in the kth clause, one of z 3k plus 1, z 3k plus 2, and z 3k plus 3 is true. So one of these is going to be true. Maybe multiple of them are true, but at least one of them is true. Take a true vertex in each clause. Now note that no vertex can correspond to the negation of another vertex. I'm somewhat abusing notation here when I mean by vertex. I mean, like, you can think of the vertices correspond to literals. So I should say that no vertex, or rather the literal corresponding to a vertex, cannot be the negation of the literal corresponding to another vertex. Right? And that's because it's a satisfying assignment. So all of these have to be simultaneously true, because there is a single satisfying assignment that makes all of these that makes one of these true. And these vertices form a clique of size m. Okay, and you'll see that the opposite side is pretty much, it's almost an identical argument, that if G has a clique of size m, if G has a clique of size m, by construction, each clause has a vertex in the clique. Okay, this is really important because note that I only connect vertices in different clauses, in different groups. I never connect two vertices in the same clause. And because of that, there are m clauses. So there are m vertices in a clique. There's one that has to be in each clause. Moreover, those vertices cannot be negations of each other. So essentially, they correspond to a satisfying assignment. Like from those vertices, you can read off a satisfying assignment. Or there exists an assignment that makes all of those vertices become true. Each clause is a vertex in the clique. All literals corresponding to these vertices can be made simultaneously true by some assignment. and hence phi is in sat. I guess technically I should say 3 sat. And that completes the proof. So any questions about this? Does this construction make sense? So the key, the heart of it is just basically this construction. And once you have this construction, then in some sense, proving the properties tend to be somewhat mechanical. Okay, the cleverness is in coming up with this construction. Any questions? Okay. So now that we have Clique being NP-complete, let's do a few more, and we can sort of build this whole web of reductions. So what I'll prove is solving a system of quadratic equations is NP-complete. Okay, so what do I mean? What is the language here? So you can think of your language would be, xi xj plus xk squared is equal to something, and x3 x5 plus x4 is equal to something, and you've got a collection of quadratic equations, and your language are satisfiable quadratic equations. Now note that solving a system of linear equations, this is in P, this is Gaussian elimination, and you've all seen this. So when you go from linear to quadratic, suddenly it jumps from P to NP complete, just the way that from 2 sat to 3 sat there is a jump from P to NP complete. And so we're going to show that a system of quadratic equations is actually NP complete, and we'll do it from Clique. So the way we're going to prove this is we show that. So I'm going to refer to this. I'm going to refer to this language. I guess I can say it's quadratic programming. Although quadratic programming does more than just this. So maybe let me call it QE, quadratic equations. That's the language, right? It's the language of satisfiable quadratic equations. And so what we're going to show is that Clique can be polynomial reduced to QE, and this is going to be a fairly simple reduction. So given, remember, an instance of Clique is G comma K. Write the system. Okay, so we're going to write a system, and then I'll explain what the system is. Summation sigma I for every vertex. This is going to be equal to K for all I that are vertices. Xi square is equal to xi. For all ij that are not edges, I just say xi times xj is equal to 0. So what happens? This condition, xi square equals xi, this is sort of the heart of it. This forces the xi to be either 1 or 0. Right? So if you have any solution for the system of equations, xi has to be either 1 or 0. This says that you need to choose k vertices that are going to be 1s. This equation says that if two vertices don't have an edge between them, you cannot make both of them 1. You can only make one of them 1. So if you have a solution, that solution is a clique. And if you have a clique, you can easily come up with the solution. Should I explain this? Should I explain this further? Explain it again? So, I'll just poll you. A for yes, explain it again. Y for no, I understand it.
Maybe you can show an example with a really small one.
I was thinking it would be nice to have a moment to digest it.
Yes. Okay. So let me show this to you for a couple minutes, and then you can go ahead and answer. I'll look at the answers. I will explain it. I think that quite a few of you would like an explanation, but I'd like you to have a look at it first. The problem with these reductions is once you get it, then it's sort of so obvious that it's true, but when you don't get it, it's sort of unclear. So please stop me if the reduction is going by too fast. All right, so let me go ahead and explain why this is the case. So what do we need to show? Okay, I'm going to kind of keep this here. Sort of refocus the image. Okay. Actually, you know what? I think I can write this side by side. It might be possible. So I'm just going to leave this over there. And all right. Okay, so we want to say that if GK is in Clique. By the way, first I should have said that quadratic QE, I guess this is maybe not as obvious, and one has to be careful about this, that QE is an NP. One needs to argue that actually if there exists a solution, then the bit complexity of it is polynomial. Let's not necessarily go into that. Technically, I'm only showing that QE is NP hard. But you can also, you can also show that it's an NP. So, okay, so if GK is in Clique, that means G has Clique, which I'll call it C, subset of V, of size K. I'm going to show you how to satisfy this system. Set for all I that's in the clique, set xi to be 1, else xi is 0. This is the solution now. Now note that by definition the summation of xi is going to be equal to k because I set exactly k things to be 1. I clearly satisfy this condition because 1 square is 1 and 0 square is 0. Moreover, I satisfy this condition. Because if you draw the picture, so here's your clique, and here are all the other vertices. I basically set all of these to be 1s and set all of these to be 0s. Now, every ij that is not an edge has to be a pair of this form. This form, or they're completely within this. Like I and j cannot be both in here for a non-edge. And therefore, for every pair that is not an edge, xi, xj is 0. So is that clear? And you should see it's easy to see the converse is also true. Like if you take a solution, then you simply take the 1s on one side and the 0s on the other, and the 1s will form a clique exactly by the same logic. So the idea is that all the variables or the vertices assigned 1 form a clique. Like that's sort of the basic idea of this construction. Okay, any questions about that?
Don't we make our own rules, like in the previous page that you said? How does the converse work? Are these like additive rules that we add?
I'm sorry, Skye, can you explain that again? Say that again.
So like let's say we get some quadratic system of equations. Like, can't some of them even be like 10? Like, why do we add these kinds of rules that we have on the left? The xi squared equals xi, and xj equals 0.
What do you mean by add these rules? I mean, I'm constructing
a not every quadratic equation or system comes with those, right?
Not necessarily, right? I mean, a quadratic system is simply like a system of quadratic equations. So what I need to show here is, given any clique problem, I can write a system of quadratic equations that is satisfiable if and only if this is in the clique, if G has a clique of size k.
Oh, okay, sorry. I thought you were also showing that from a system you could go to a... Never mind, yeah.
I'm not going the opposite direction.
Yeah.
I'm not reducing quadratic equation to clique. I'm reducing clique to quadratic equation. So is this clear? Like, please, I'm gonna pause here, and I'm gonna take any questions about the previous reductions that I've shown. So I'll just pause the recording. So I also want to, emphasize like how amazing this entire, now that we've reached this point, how amazing all of this is, because you could imagine like people have been solving linear systems of linear equations for I guess a century, and people have known that systems of linear equations can be solved efficiently, and it's natural to ask, okay, what if you have quadratic equations? And people got stuck. There was a barrier. They were not able to solve quadratic equations efficiently. And now we have sort of an explanation, but the chain, we're basically saying if you can solve quadratic equations efficiently, you can solve any problem in NP. Not just, not just SAT, but really any problem in NP. And you can do that because we were able to use Cook-Levin to go from any problem in NP to SAT, use the normal forms to go from SAT to 3-SAT, then from 3-SAT we went to Clique, and then from Clique we went to quadratic equations. If you actually tried to chain all of those reductions together, it would be incredibly complicated. But what this is saying is quadratic equations can effectively simulate the non-deterministic Turing machine, right? Because that's what, if you think about the whole tableau method, we were basically trying to represent the behavior of a Turing machine using a Boolean formula. And what this is saying is you can also represent it with a system of quadratic equations, but you cannot do it with a system of linear equations. Right? So mathematically, this is like, there's a big aha moment here. Like, you suddenly discover that quadratic equations are much more powerful than linear equations. So let's see, I want to give you another example of such a problem, and then I want to do a more like complex reduction, and then we'll try to, we'll go back to all of these things at the end. So now let's talk about a very important language called integer programming. So this is, you may have heard of something called linear programming. You may have heard of something called linear programming. So linear programming means a system of linear inequalities. And you want to basically solve a system of linear inequalities, not equalities. So solving a system of linear equations is Gaussian elimination. To solve a system of linear inequalities is actually a much more challenging problem. It turns out that this language is in P, but that's a very non-trivial result. And this was, discovered in the 70s by Katya, and this is not an easy result, but it turns out linear programming is in P. Now, what is integer programming? Integer programming, it's a system of linear inequalities where variables are integers. So we force the variables to be integers. And you can already see that the quadratic program that we wrote is very similar, has this flavor, because this quadratic condition simply forces xi to be an integer. Although this is a quadratic constraint, it's not a linear constraint. But what we'll show is that actually you can get all of these by linear constraints as well. You can get all of these by linear constraints. And there are multiple ways of doing this. There are multiple ways of showing that integer programming, and I'm just to be safe, let me not make claims about it being an NP, because then I'd have to argue maybe about bit complexities, and I don't. While all of that can be done, I don't want to go down that route. So I'm just going to argue something simpler. I'll just say that 3-sat can be reduced to integer programming, and it turns out the reduction is really straightforward. You can take each clause, and you can convert the Booleanness to basically an integer linear inequality. And so given phi, which is a 3CNF, for each clause I'll say xi or xj negation or xk, write the inequality xi plus 1 minus xj plus xk is greater than or equal to 1. Right? So write down all of these inequalities and then just say that for all I, xi has to be in 0 or 1. So this is just saying that you're taking the truth value and you're replacing the OR condition by just an addition. And again, the reduction should be clear. Like I'm just going to end this and say that the exercise finish the details. Which is to say that if there's a satisfying assignment, these equations can be satisfied, and if these equations can be satisfied, there exists a satisfying assignment, and it's pretty straightforward. So what this says is, even the language where the variables are, forget integers, but just 0, 1, even this is NP-complete. And this is again important because there are lots of optimization problems where you get inequalities of this form, where you're trying to allocate resources, and people are studying these problems from the 50s and 60s and trying to get solutions, and they were unable to get efficient algorithms. And then the theory of NP-completeness in the 70s starts explaining why that's the case. Because it says that if you can solve integer programs, then you can solve any problem in NP. Now let me give you another reduction, and this is a really clever reduction. So by the way, I should say that a lot of these reductions were given by Karp, and I believe it's maybe it's 71 or 72, who gave a list of 21 NP-complete problems. So it was Karp who took this Cook-Levin theorem and then applied it through reductions and showed that a whole host of problems are NP-complete. Many of the reductions that I'm showing are actually from Karp's original paper. And it was Karp who, was one of the, and Levin also did this on the other side of the Iron Curtain. So Karp and Levin really showed how that theory of NP-completeness, how the Cook-Levin theorem, which seems like something esoteric, suddenly starts connecting to lots of problems in optimization and lots of problems that you'd be, the graph problems you'd be interested in. So now let me give you another classic problem, which is Hamiltonian path. So a Hamiltonian path is a path that visits all vertices exactly once. So it is a path that visits all vertices exactly once. That's a Hamiltonian path. And so now the question is, can you find a Hamiltonian path? A path that visits all vertices exactly once. So if you're given a graph, a Hamiltonian path should never cross itself, so that's not allowed. What it needs to do is to basically go through all vertices exactly once. And a Hamiltonian cycle means that it sort of has to return. So it would be a cycle that visits all vertices exactly once, where a cycle is basically just a path that comes back to itself. So let's look at the language that I'll call D-Ham path. So this is directed Hamiltonian path. So G is directed, and G has a Hamiltonian path. And so our theorem is that the directed Hamiltonian path is is NP complete. So firstly, directed Hamiltonian path is an NP, and the certificate is the path, which is easy to verify. Right? If you're given a potential path, you can easily check if this is a Hamiltonian path. Just check if all of those are edges, it doesn't visit itself, and it visits all vertices. Now for the construction, we're going to do something called a gadget construction. Now we already did a gadget construction for the cliques. So think of this is called a gadget because what it says is you convert every clause into a set of vertices. But here, it's pretty much it. There's not much more than just this for the gadget reduction. Here what we'll do is we will convert every variable into a particular small graph and every clause into a small graph and kind of join it all together in such a way that this is going to give us the final constructions. Okay, so we're going to actually reduce 3-sat. So we're going to go directly from 3-sat to Hamiltonian path. So let's just say phi has, I'll say, k variables. I don't want to use n because n is the size of the instance, and m clauses. So for each variable, construct the variable gadget. And what is the variable gadget? So we're going to construct the following graph. We're going to put 3m plus 2 nodes here. 3m plus 2 nodes over here. We're going to put an edge from here to here, there to there, and sorry, it's not 3, but sorry, 2m plus 2. Okay, and then we're just going to put edges that go back and forth between this. Okay, so you have a chain of 2m plus 2 vertices in the middle, and then you can go this way or you can go this way. So now think about a Hamiltonian path. A Hamiltonian path, if it's going to cover all these vertices, takes this path and then goes all the way here and then goes that way. Or it goes this way, it goes all the way there and then goes this way. Right? So it basically has these two ways of going, either left or right. And we are going to use the left or right to encode whether this variable becomes true or false. This is very clever. We're going to use this, the fact that there are two Hamiltonian paths within this little gadget, to encode whether a variable becomes true or false. So this is what you do for each variable. Now what you do for each clause is clever. So each clause is a vertex that I will call Cj. So there are m clauses, and each of those is going to be a vertex Cj. Now here is what I'm going to do in the construction. So let's just say that, suppose the clause j, suppose the jth clause is xi or negation of xj or xk. I'm going to show you how to connect these together. So remember, there is this gadget for xi, xj, and xk. Right, so this is, I'll just say, is xi, xj, xk. Now in the middle, if you recall, there were two m plus 2 vertex nodes. There are two m plus 2 nodes. So I'm going to ignore these two nodes, which gives me two m nodes. And I'm going to say, I'm going to mark this as 1. This is 2. I'm sorry, so 1. Let me sort of blow this up, and then I'm just sort of blowing up this thing. Okay, so let's just say it started here, and it's going on. Remember, this I'm just going to sort of block off for convenience. This I'm going to refer to as 1. This is 2. This is 3, so on and so forth. So these two will correspond to clause 1. These two will correspond to clause 2. These two correspond to clause 3, so on and so forth. Now I'm going to find the two vertices that correspond to j. My convention is going to be, remember I said one of these is true and one of these is false. So I'm just going to think of this side being true and this side being false. So this going this way is true. Starting here and going towards the left is true, and going towards the right is false. So because starting here this is true, and if xi is true, the clause is true, I'm going to put these two edges. Now for x, okay, so this is poor notation on my part. So instead of calling this the jth clause, let me call it the bth clause. Okay, because I have ijk over here. Okay, now let me look at what happens to j. Now j behaves differently. When j is false, the clause is satisfied. So again, I'm going to take the two vertices corresponding to j, but I'm going to go in the opposite direction. Instead of connecting from this vertex, I'm going to connect from this vertex. I go there, and then I go there.
I think I see where this is going. Can I
Yeah, so let me, yeah, sure, let me just finish this and then I will ask you. And then I go from here. Now remember, when k is true, so therefore I go from left to right, I do this. So this is now my construction. So I have these vertices for all the clauses, and I have all these clause gadgets here. And I simply connect up all of these vertices to the gadgets using this mechanism. Okay, now go ahead.
So essentially, in one of the variable gadgets, as you had already said, of course, like the way that it chooses to go encodes whether it's true or false.
Mm-hmm.
And in effect, if you choose one direction, then you're allowed to have it also veer off and visit a clause to include it in the Hamiltonian path.
Yes.
But only if like it corresponds to like whether it's negated or not negated as a literal.
Yes.
And yeah.
Exactly. So you're exactly right. So what you're seeing is you've essentially proven one side. You're saying that if phi is satisfiable, there exists a Hamiltonian path. Because you'll say that using the satisfying assignment, whether it sets each variable to be true or false, you will simply follow that direction and visit all those clauses, and thereby all the clauses will be visited and all the vertices will be visited. So you're absolutely right. So that is the proof of one side. The other side requires more care. What you need to say is, if there is a Hamiltonian path, then there exists a satisfying assignment. Now the problem is, what if your Hamiltonian path went from one gadget to a clause and then skipped and went to another variable? If it's hops between variables, then it seems like there's a problem. Except in those cases, you can argue that there doesn't exist any Hamiltonian path that does such hops. Okay, so this is a complex reduction. So let me write things out more clear. So the first question, do you understand the reduction? Do you see why the reduction is efficient? How many vertices are there in this reduction? How many vertices? So remember, we said if you have k variables and m clauses, k variables and m clauses, how many vertices do you have in the end? With big O's. Right? Remember that each clause gadget looks like this. So how many variables do you end up with?
O of mk.
O of mk, exactly, right? So the total number of variables is O of m times k. So, and clearly this graph G, so I'm just going to refer to this as G. G can be constructed in polynomial time from the encoding of the assignment of the Boolean formula, right? So given your CNF, your 3 CNF, it's easy to construct because you would basically write down, you could create all these vertices, create all the gadgets, connect them up appropriately, and it's going to be of polynomial size. Okay, so now we need to prove two sides. We need to prove the first claim is if phi is satisfiable, then G has a Hamiltonian path. So consider satisfying assignment. So there is some satisfying assignment, and let T be the subset of true variables and F be the subset of false variables. So T is a set of true variables, F is a set of false variables. For each clause, assign an arbitrary variable, that makes the clause true. Note that that could be a variable in T, or it could be a variable in F, because there could be a clause where setting something to be false makes that true. There could be multiple variables that make it true because it's an OR. Just assign one of them arbitrarily. But the fact is you can always assign something, and this is the key. Because this is a satisfying assignment, this assignment makes sense. That for each clause you can find a variable that makes it true. Is this clear? Just to be formal, I'll say for each, now I'm going to, for each variable x, let C of x be the set of clauses assigned to x. Okay, so what is the Hamiltonian path going to do? The Hamiltonian path will traverse each gadget for a variable in T by the left and each gadget for a variable in F by the right. What this means, and as I said earlier, was that for a variable that is going to be true, we will go this way. We will go to the left. We'll go to the left and then traverse in this direction and then go back. For a variable that is false, we traverse in the opposite direction. Okay, for every variable, we traverse in the opposite direction. Moreover, just recall what C of x is. I'll say that the path through the gadget for x visits all the vertices in C of x. Now, you need to sort of verify that this construction yields a Hamiltonian path. But hopefully this construction makes sense. So at this point, I don't want to belabor the point and give more detail. I think the key is to look at the picture and get the idea. But this gives you one side of the reduction, right? It only says that if phi is satisfiable, then G has a Hamiltonian path. And the key is, and as this was mentioned before, is that essentially all the ones that are true, the variables that are true, they can visit their clause in one direction. The ones that are false will visit their clauses in the other direction. Each clause will be visited only once, right? Because we ensured that we did a unique assignment. We did a unique assignment. We don't assign a clause to all the variables that make it true. We assign it to one of them. Assign an arbitrary variable. I should say a unique, just to be precise over there, is a unique arbitrary variable, any of them that makes it true. And this way all the clauses will be visited and all the vertices in here will be visited as well. Because, as was mentioned, what's going to happen in this path is it will keep traversing this and then periodically make detours to visit the clauses. And this ensures that all the vertices are visited. Are there any questions about this? Please ask me if, does this make sense? I'm going to poll you and ask you. So A is yes, this makes sense, and B is no, it doesn't, it makes no sense. So B is like, this makes no sense. A is, yeah, it's starting to make sense. You'll have to stare at it a bit just to make sure, but.
Can I ask a question?
Go ahead.
By all the vertices, do you mean all the vertices in all the gadgets plus the clauses, or just the clause vertices?
In which all the vertices?
When we're at the Hamiltonian path, which vertices are they traversing? Because if you look at the gadget description, the bottom vertex in that diamond you can never reach that. I was a little confused, what the Hamiltonian path is. Is it just
Oh, I'm sorry. No, you're absolutely right. So I have not. Okay, you're right. Sorry. Good point. I need to complete this construction as follows. Yeah, you're right. Sorry. What I'm going to do is so let's say this is the gadget for variable x1 and this is the gadget for variable x2. I would just connect it in this way. And this would be for x3, so on and so forth. This is just to ensure that once you exit one variable, you enter the next variable. Thank you. That was I forgot to mention that. Right? And so this enters from here and goes out to the next gadget. Right? So we're going to start at x1 and we're going to end at your final whatever xk or xn.
So is it true that without, regardless of the clause nodes, there's always a way to get from all the gadgets to traverse all the gadgets? Is there, disregarding the clauses?
You're right, exactly. So if you can always, it's easy to get a path that visits all of these vertices and ignores these.
Gotcha.
Right, because
so the clauses are the key then.
I'm sorry?
The clauses are the key.
The clauses are the key. The clauses are the key, exactly.
Gotcha.
And we haven't completed the proof yet. There is a tricky part. The tricky part is to say if there exists a Hamiltonian path, then there exists a satisfying assignment. Now it seems like, the proof is just the same, right? You could take any Hamiltonian path and it goes either to the left or to the right. But now you have to be careful. How do you know that your Hamiltonian path is not going to go to a clause and instead of coming back the way it should, it actually jumps and goes to another clause, another variable, I'm sorry. So the way you set the Hamiltonian path, you want it to go from a variable gadget to a clause and come back. This you can enforce in the if direction because you're constructing your Hamiltonian path. But on the other side, if you say if there exists a Hamiltonian path, there exists a satisfying assignment. So you want to ensure that when your path goes to a clause, it returns to the variable where it came from. It doesn't jump to another clause. It doesn't jump to another variable gadget. So when you want to argue that if you have a Hamiltonian path, when the path goes from a variable gadget to a clause, the path must return to the same variable gadget. Is that clear what I just said? Please ask me, please clarify if that is not clear, if what I said did not make sense.
So there's only ever one. If a clause is true, there's only ever one path from the gadget from any of the three gadgets to the clause. Is that correct?
No, if it's okay. So let's take this clause over here. Let's say the satisfying assignment made xi true, xj false, and xk true. Then that gives you three options to visit that vertex, to visit the clause vertex.
I thought you said that we would choose that we would only select one of the true variables.
Exactly.
To have.
Yes, I just wanted to emphasize that we will choose only one of them. But then once you choose one of them, there's only one way to get there.
Oh, is that for choosing like the actual path?
That's for choosing the actual path.
I see.
Because you don't want to have multiple variables taking detours to the same vertex, because then it won't be a Hamiltonian path anymore.
Right. Gotcha.
Almost like a parallel question.
Yes.
These vertex gadgets, if I'm saying it correct, or variable gadgets, are they unique? Are they for each clause? Do we have them like Z's, or is it in variables in general? Because
variables in general, just one for each variable.
Okay, so then can we have situations where like a variable is true and implies both like multiple clauses?
Yes, exactly.
Maybe you could expand the uniqueness part that you talked about.
Okay, so the uniqueness is one way, right? It says that, but each variable has a set of clauses that is assigned to it, and the path will visit all the clauses. And how is it going to do that? Remember that if you look at the actual path in here, there are sort of two vertices that are specific to each clause. So what it does is, either it doesn't make a detour, it just hops over to the next one. But if it sees a clause that is part of C of x, the one that is assigned to it, then it makes the detour. So it makes the detour for everything that is assigned to it.
I think the confusion might be that in one of our reductions, we had constructed a graph which had duplicates of a variable. But
right.
This one we won't.
This one we don't, right. So I think in the Clique example, we actually had one variable for each occurrence of a literal. And here we only have one variable gadget for each variable, not even each literal, right? Like just each variable, because we already encode within here true or false. Alright, so I am not going to necessarily, again, I think that at some point you will have to go back and stare at the construction to sort of convince yourself of all the details, and there isn't as much value in me explaining it in sort of gory detail. But if you have any questions, feel free to come to office hours or in the next lecture if you want me to go over that again. I'm happy to talk about it. And remember, there is another claim that one has to prove, that if G has a Hamiltonian path, then phi is satisfiable. And as I said, the argument is not as obvious. You have to be careful, because a Hamiltonian path might be doing weird things where it jumps to a clause from a variable, then jumps to a different variable. But you can show, given the construction, that that cannot happen. So any Hamiltonian path is going to sort of faithfully encode a it's going to faithfully encode a satisfying assignment. So I want to mention something here which is very intriguing. So if you look at, there is another problem known as the Eulerian path, which is a path that visits every edge exactly once. Right? A Hamiltonian path visits every vertex. An Eulerian path visits every edge. And again, remarkably, this problem is in P. It's actually an exercise from CLRS. It's like a 101 exercise. You can do it basically with like some DFS. So visiting every edge is in P, but visiting every vertex is NP-complete. And I should say that I did this for Hamiltonian path. You can also get it for Hamiltonian cycle. Again, you can show that it's NP-complete. You can actually reduce Hamiltonian path to cycle. Actually, you can actually just use a similar reduction over here, a similar reduction over here, and then what you do is in the end you kind of sort of connect it back to get a cycle. So it's fairly straightforward. You can also prove that undirected Hamiltonian path. So this is, we did the directed version. This is NP-complete. And again, I won't give you the proof. I'll just give you a proof sketch. What you can do is you reduce directed Hamiltonian path to the undirected version. And there is a trick that's called vertex splitting. And this is sort of a useful trick to know in general for graph algorithms, which is in a directed graph you have a situation like this. You simply convert that to two vertices that have this structure. So if you have a vertex V, you create two copies called V in and V out. And then you can essentially convert a directed graph to an undirected graph, and then Hamiltonian paths in the directed graph will correspond to Hamiltonian paths in the undirected graph, and vice versa. So in this case, the paths are actually equivalent. And this would show that undirected Hamiltonian path is NP-complete. Okay, so let me, let's pause here. Let's take a breath for a few minutes. And then I'll do, the last reduction for today. But, ask me questions. So I'll continue maybe with, and I'll do one last reduction. Again, there are lots of reductions, and, many books cover many of these reductions. And I just wanted to do a few of you to give you a flavor of the kinds of techniques that are there. And also, because your homework has, some reductions to do. And the best way to get used to these reductions is to just do more of them, is to gain practice. And Aurora Barak has an excellent collection of questions. So do some of the more basic textbooks like Hopcroft, Motwani Ullman, and Sipser. So let me talk about another language that's called set cover. So what is set cover? This is unlike the graph problem, this is like a very sort of combinatorial problem where, so consider a universe U. So this is just a universe, some sort of finite universe U. A collection of sets S1, S2 to Sk is a cover if the unions, so these are all sets, these are all subsets of the universe, right? This is just you have some universe of objects and you have sets in this universe. If the union of all these sets is the universe, that's called a cover. And so this problem is called set cover. So, okay, what is the language set cover? So let me suppose you now have, let bold S is a family of sets, and set cover is the language where you have a family of sets and a value k, and you say that S contains a cover of k sets. So that's just saying that a k is overloaded here. So let me call that B. So think of it like it's just saying, what is the smallest cover that you can construct? And set cover is saying that it's, this is like finding the smallest cover. So set cover says, is there a cover of k sets? Just like clique was like, is there a clique of size at least k? Set cover is there a cover of size at most k? A cover of at most k sets. Right? Because if you have a cover of less than k sets, then you can just add more sets and it would still remain a cover. Okay, is the language clear? What this language is? So, and the theorem is that set cover is NP complete. So for the proof, what we'll do is we'll just say that set cover is in NP, and the certificate is just, certificate is just the list of sets in the cover. In the cover of at most k sets. Right? So that's the fact that it's in NP should be fairly straightforward. And now let me prove that 3-sat can be reduced to set cover. Okay. So let me first tell you what the universe is. The universe is going to be all variables. So just think of the universe, just all variables. And a vertex for all clauses. As an element for all clauses. So this is just sort of syntactic, right? I'm going to construct a universe where there's one item in the universe for every variable, one item in the universe for every clause. Now construct the following set. So for each variable I'll say for the ith variable, construct sets T of I. So T of I is going to be xi, and I'll just say C1, I'll say CI1, CI2 to CIR. These are the clauses made true by xi being true. These are the clauses made true by xi being true. Fi is this is somewhat poor notation on my part because I'm overloading xi being the variable and an item in the universe. So I'm just going to put a hat over here to denote that it's just an element of some universe. I'm just going to put a hat over there. So this is also going to contain x and hat, and this has cj1, cj2 up to cjl, where these are the clauses made true by xi equals 0. So for each variable, I can look at the clauses that it makes true when or for each variable, I look at the clauses that are made true when I set that variable to true, set it to 1. That's some list of clauses. I just put those elements in the set. And then I look at the ones that are made when I set this to false, I look at the clauses that are satisfied, that are made true, and I put the elements corresponding to that in the set fi. Okay, so now my instance, so what is going to be the collection of sets? So I have a family of sets, and that's just going to be T1, F1, T2, F2, up to Tn, Fn. Or I call this B. Okay, that's how many variables there are. Okay, my universe, as we said, was y1 to y, were all of these. And now my instance, I'm just going to say that my instance is now going to be this family, comma, b, the number of variables. This is the number of variables. And so if phi is in 3-sat, the fact that it's 3 is actually not even that important, but if phi is in 3-sat, then S has a cover by picking exactly one of Ti and Fi for all I. So for each I, if I simply take the one that the satisfying assignment is, so satisfying assignment made xi to be true, then I would take this set. If it made xi to be false, I would take this set. And if I took all those sets, the union of all those sets are going to satisfy all the clauses. And you can also argue the converse. You can say that if F has a cover of B sets, then phi is satisfiable. And that again you argue because there's this element xi hat, and if there's a cover, the cover has to pick either Ti or Fi or both of them. But if it picked both of them, then it would end up with too many sets in the end. And so again, you can make this argument. And that proves that set cover is NP-complete. Now I want to leave you with sort of a very, very intriguing statement given the NP-completeness of Hamiltonian path. So, and the intriguing statement, this is actually why Gödel thought about NP-completeness, or the notion of NP in the P versus NP question, where he said the language he was interested in was sort of in meta mathematics. So consider the following language. I'll say C, comma 1 to the t. So C is a mathematical theorem. So think of it as the encoding of a theorem. It could just be the statement of the Riemann hypothesis, stated in mathematical language. That has a proof of length at most t, where the length can be measured in symbols. So this, in some sense, is the language of all true mathematical statements, but you also sort of append it with how long the proof is. And you can convince yourself that L is an NP, right? Because the certificate is the proof, and a proof can be mechanically checked. And this is how Gödel got into this. Proofs can be mechanically verified. Right? So you can always check a proof by just making sure that it goes from one statement to the next, following the rules of logic. And all of that can be mechanized. Now, because this is NP, and remember that Hamiltonian path is NP-complete. Therefore, given any mathematical statement and a bound on the proof length. And a bound t on the proof length, we can construct a graph of poly t size such that, so given any mathematical C has a proof of length at most t if and only if G has a Hamiltonian path. So this is, if you think about it, this is absolutely bizarre. So given, let's say, we know Fermat's last theorem is true, but given the Riemann hypothesis or any unsolved problem in math, and given some bound on how long we want the proof, we want to see, is there a proof that's going to be 100,000 characters? Given that, so given this bound of 100,000 in unary, of course, and the mathematical statement, we can actually construct a graph. And the procedure is essentially described in whatever we've done so far. We can construct a graph, and the graph is going to have a Hamiltonian path if and only if the statement is true with that proof length, or there is a proof of that length. Which is why actually we think that P would not be equal to NP, because if P was equal to NP, then we would actually have a method to essentially prove theorems by just constructing them into graphs and then searching for Hamiltonian paths. So I will leave you on that intriguing note, and when we come next time, we'll talk about co-NP and other complexity classes.